Sample problem 15.10. At elevated temperatures, iodine molecules break apart to give iodine atoms according to the equation I2 gas turns into 2I gas. Kc for this reaction at 205 degrees Celsius is 3.39 times 10 to the minus 12. Determine the concentration of atomic iodine when a 1.00 liter vessel originally charged with 0.00155 moles of molecular iodine at this temperature is allowed to reach equilibrium. Okay? So this problem is not that different from 15.9. So I2 can break up into 2 iodine atoms. Looks like a pretty simple reaction, right? One molecule just breaks up into 2 atoms. And it tells us that the equilibrium constant Kc is 3.39 times 10 to the minus 12. They then give us the initial amounts. Now, in this problem, they give us the initial moles, not the molarities. But to find the molarity, you just take the moles and divide by the liters. So the initial concentration of molecular iodine, I2, the initial concentration, would be 0.0155, oh sorry, 0.001, let me erase that. .01, sorry, 0.00155 moles divided by 1 liter. Remember, molarity is concentration in molarity units is just the number of moles divided by the volume in liters. So that would be 0.00155 moles per liter. Okay? All right, so let's put that in here. I'm going to actually put that into scientific notation. 1, 2, 3. 1.55 times 10. To the right, if you move the decimal to the right, it becomes negative. If you move it to the left, it becomes positive. So 1.55 times 10 to the minus 3. Now, the initial concentration of iodine, atomic iodine, atoms, is 0 because they didn't add any in there, so that must be 0. Okay? So how do we deal with this? Well, remember, we do Q. Q is the concentration of the product, so that's 0 squared over the concentration of the reactant, which is 1.55 times 10 to the minus 3, right? Products over reactants, that's 0. So Q is less than K, which means the reaction goes to this side, so you get plus 2x on that side and minus x on that side, right? It's negative on the side it's going from, and positive to the side it's going to. So minus x plus 2x, and then at equilibrium, this would be 1.55 times 10 to the minus 3 minus x, and this would be 0 plus 2x, which is just 2x. Okay? So there we go. Now we set it up just like we've done before. So Kc is 3.39 times 10 to the negative 12, and that would be equal to, again, products over reactants. So 2x squared, don't forget this squared, right? 2x, but then because of the way we define the equilibrium constant and the reaction quotient, we have to raise it to that power. And then that would be divided by this. 1.55 times 10 to the minus 3 minus x. Okay? Okay, again, we cannot take the square root of both sides because in the denominator, it's not to the squared term. Okay? So that means we're going to distribute. So we're going to take what's in the denominator, multiply it by k, and that'll be equal to what's in the numerator. So let's do the numerator first. I'll do it over here on the left. 2x quantity squared is not 2x squared, it's 4x squared. And that would be equal to 3.39 times 10 to the minus 12 times 1.55 times 10 to the minus 3 minus x. Okay? Distribute that value of k. So you get 4x squared equals 5.255 times 10 to the minus 15 minus 3.39 times 10 to the minus 12x. Okay? All right. I've got the x squared on the left side, so let's move everything to the right, to the left. So I'm going to subtract this from both sides. I'm going to add this one to both sides, right? If this is minus, you add it, so that makes it 0. If this is plus, then you make the minus, so that makes that 0. So now you're left with 4x squared plus 3.39 times 10 to the minus 12x minus 5.255 times 10 to the minus 15, right? I see what happened. This is 15. Minus 15. Okay, and that's going to equal 0. Okay? So again, as we do these sorts of problems, we have to just I'm going to have to get rid of a lot of stuff here, all this work that we're doing. Okay. So we now have it actually set up as a quadratic equation. So again, quadratic formula, x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Okay. So our a is 4. Our b is 3.39 times 10 to the minus 12. And our c is negative 5.255 times 10 to the minus 15. Okay. So let me come up over here and let's do this. X is equal to minus b. Well, b is 3.39 times 10 to the minus 12, so that's minus 3.39 times 10 to the minus 12, plus or minus the square root of that number, 3.39 times 10 to the minus 12 squared, minus 4ac. A is 4, and then c is minus 5.255 times 10 to the minus 15. And then that's all over 2a. Okay? All right, so now we can get rid of this down here. Okay, so how do we simplify this? Well, remember, you're going to square what's in the b squared. You got to square that one. And then you're going to subtract 4ac from that. So we got minus b. And then you get the square root, plus or minus the square root of 8.407 times 10 to the minus 14. And then over 8. Okay. Now, when you're doing the radical, remember you're subtracting 4ac, but c is negative. So subtracting a negative number is like adding a positive. So what you're going to do is you're going to take that b squared and you're going to add it to 4a and make C a positive. So you get a positive number in the radical. Okay. So let's go ahead and take the square root of that. When you take the square root of 8.407 times 10 to the minus 14, you get around 3 times 10 to the minus 7. So x then becomes minus b plus or minus 2.899 times 10 to the minus 7. And then again, that's over 8. Okay, so now we have two solutions to it. We have the solution positive and we have the solution negative. So let's do the positive one here. I'm just going to do the minus b plus the 2.899 times 10 to the minus 7, and then divide that total by 8. Remember, you got to add it equals and then divide by 8. Don't add it and then divide by 8. Your calculator will think that you're just taking the second number divided by 8. So when you add those together and then you divide it by 8, you get 3.62 times 10 to the minus 8 molar. And then you do the negative root. Now you have negative 3.39 times 10 to the minus 12 minus 2.899 times 10 to the minus 7. So you get negative 3.62 times 10 to the minus 8. We're going to pick the positive root. And the reason for that is that if you pick the negative root, that would tell you up here when you get to equilibrium that this is getting bigger. But that can't be the case, right? If you subtract the negative, that's adding a positive. So that can't be right because that would mean that I2 is getting larger. But we know I2's got to get smaller. So it's got to be this positive root. That's got to be our answer right there. Okay. So again, let's make some room over here. And we're just going to use the positive root. Okay. So concentration of I2 at equilibrium would be 1.55 times 10 to the minus 8 minus, minus 3, my mistake. .62 times 10 to the minus 8. Now, if you run that through your calculator, you're going to get 1.55 times 10 to the minus 3. And the reason for that is this is so small compared to this one, right? 10 to the minus 3 is so much larger. It's 100,000 times larger than 10 to the minus 8. So for that reason, if you're subtracting something that's so small, it's just going to show up as subtracting 0, okay? So you'll get the same number, 1.55 times 10 to the minus 3. That's actually looks to be close to what we started off with. Concentration of iodine, on the other hand, at equilibrium, this is at equilibrium, is 2x. So it's 2 times 3.62 times 10 to the minus 8. So you get around 7.24 times 10 to the minus 8 molar. And there's our answer there. Okay, 3 sig figs. Do we need 3 sig? Yeah, I guess we need 3 sig figs. Okay, so let's check our answer. Is this going to be equal to K? Well, you would put in the concentration of atomic iodine that you just calculated and square it. And then divide that by the concentration of the molecular iodine. And you check it. And you see what you get. And so doing this calculation looks like it comes out to about 3.38 times 10 to the minus 12. Well, that's pretty darn close, right? That's almost what we got there for K. So Q is pretty much equal to K. So that means we're at equilibrium. And that means we did our calculation correct. That last bit there is a little check just to see if you got the right answer. The fact that it comes out to the same value as K means that you got the right answer, okay? Now your textbook does show in here a solution of a little assumption where what they do is they say, hey, when you solve for x, you can simplify it by ignoring this minus x here. I'm going to ignore that analysis for this problem because they don't even tell you any justification for that. When we look at some problems in chapter 16, we'll look at it a little more formally and do a justification for it, for why we can do that. It does simplify the problem dramatically, algebraically, and so it is something we'll want to look at in the future. But for chapter 15, again, no justification, no valid justification is given for that. So I'm just going to use the same technique that we've learned from the previous example.